Well, that was a wonderful 30-minute tour through non-X-rated stellar astrophysics. And after the next speaker, we'll have Mike back for a 5-minute encore to show you the real promiscuity. Our next speaker is Dimitar Sasselov. He is a professor of astronomy at Harvard and a member of the Harvard Smithsonian Center for Astrophysics. He's a native of Bulgaria. Has 2 PhDs. The story, as I understand it, was that he was, prior to the fall of the Soviet Union, in and around Sofia, was accepted at the University of Toronto to begin studies for PhDs. Couldn't get an exit visa to get to Canada, so he began his studies at Sofia. Then the Soviet Union fell, so he was able to make his way to Toronto. He decided to take a PhD at each place. Why you need 2 PhDs, I'm not sure. It's probably not even recommended. But he is a stellar astronomer. I've described him in the promotion materials as a planetologist, not a paleontologist, but a planetologist. But he is at heart really a stellar astronomer. He's been pioneering much of the work concerning the search for extrasolar planets, planets around other stars, maybe even alien worlds like our own. And he's also heading up and spearheading the work at Harvard concerning the new Origins of Life program, which sounds very, very exciting in the next decade. So please welcome Dimitar Sasselov as our next speaker. That was great. Very good.
Sorry, but I have to change the X-rated part. There we go. Thank you, Eric. It's a pleasure to follow, and a difficult task to follow in the steps of the great talk that Mike Shara just gave you, but it is the proper step in the cosmic evolution story that you started hearing here a week ago and will continue for the next 2 weeks. After stars and planets are those very special, at least to us, objects in the universe which allow complex molecules to come together and produce the miracle of biology. So what I want to tell you about tonight is some of what we know about how planets form, how do they survive, why are they so diverse, so many of them of different types, sizes, and makeup, and why some of them, we believe, are going to be just like our Earth, habitable or hospitable to life as we know it, or maybe especially interesting to life as we don't yet imagine and know. So the journey which I want you to take with me is really a journey we have started now to look for environments which we can call home, like the planet which you all know very well, planet Earth. Why I said that this journey has now begun is because just 10 years ago we actually had very little direct knowledge of planets around other stars. We hoped that there are many planets around other stars, but we had no direct knowledge of that, no evidence. And it is only 10 years now that we have evidence, and that evidence has piled up quickly to the point where we know of many planets around nearby stars. And in fact, most importantly, we now have about 18 multiple planetary systems which resemble to some extent our own solar system. And I'll have more to say about that. So in a way of giving you an outline of my talk, I will actually follow in my presentation these 3 basic questions which have come out as the most interesting, important main questions of that new field, the field of the study of planets around other stars. And by implication, of course, planets or system. This is really the plan of my talk, and I would start by telling you about planet formation and how survival as well. That is, what do we know about orbits of planets? To some extent, this first topic is really due to the big surprises encountered when we first discovered planets around other stars. 10 years ago, that wouldn't have been such an important point to discuss with you, because 10 years ago, we had a very, we thought, good and working model, which explained very well one example of a planetary system. It had a very venerable history. It was called sometimes the Kant-Laplace model of planet formation and the cosmogony, the formation of the solar system. It was 250 years old and explained everything. So there was little that we needed to add to it, we thought. And then 10 years ago came the discovery of the first exosolar planets, and then very quickly a few more, and now up to 168. One of those first planetary systems to be discovered was a fairly bright star. You can see it actually in the winter sky. It's Upsilon Andromeda. It has 3 planets that we have detected so far. We know of 3 planets around that planetary system. And here I want to compare it for you to the solar system in terms of orbits. So what you see here is a schematic picture of the orbits of 3 of the planets that we know circle the Upsilon Andromeda, which is a solar-like star, and then some of the solar system. Of course, you all know that this is not the entire solar system, just the inner part of it, but this graph is to scale. And there are 2 things that you will notice here, which from the very beginning puzzled everybody in the field, including the people who discovered the new planets, and in a sense have produced a new paradigm, changed our understanding of planet formation that we had before that discovery 10 years ago. The first fact that you see here is that the planet as massive as Jupiter, the blue orbit on the left side, where you see the Upsilon Andromeda system, has a very eccentric orbit, similar to, and actually much more eccentric. It's not circular, it's a very elongated ellipse, much more so than Pluto in our own solar system has, and certainly reminding us more of the orbits of comets rather than a planet. That's one of the problems. Most of those planets that have been discovered so far have very eccentric orbits, more so than we would expect from our very orderly, almost circular orbit-like solar system. The second big surprise, and that was actually a surprise which occurred right away, the first exosolar planet was one of those unusual planets, is the little red planet right smack next to the star. You might have thought that it's some artifact on the graph, but it's actually a planet with a very, very tiny orbit right there in the center. This planet is like Jupiter. It has the mass, the size of planet Jupiter, yet it is right next to the star. It's called, appropriately, a hot Jupiter. That is a Jupiter which is very hot because so close to the star. Virtually, you can think of the star as being an orange in my left hand, and Jupiter will be a grape right that far away from it. So this is Upsilon Andromeda A, or Upsilon Andromeda B, which is the red planet right next to the star. Now, in the old planet formation theory that we had 10 years ago, that was an impossibility. Or I should say better, nobody had thought of it, and people should have. But nobody had even imagined that there would be a Jupiter, large Jupiter-like planet in an orbit so close to its parent star. Partly because in our solar system, Jupiter is very far away from the sun. It's actually not on this picture. It's about 5 times further away from the sun than the Earth is. And its orbital period is 12 years. The orbital period of that star down there is 4 days. Very different place to live, and certainly very hot one. So this is what a hot Jupiter orbit looks like in comparison to the orbit of the Earth. So that's another of those newly discovered planets in the last 10 years. That one was discovered 6 years ago. All of them have very unromantic telephone number names. Don't ask me why, but, well, you can ask me, but I can't do anything about it. They will remain nameless, but not numberless. So this one is a very special one because it is very well studied. And its orbit, as it befits now to this new class of planets, hot Jupiters, is really very, very close to its parent star. The parent star, again, is very similar to our own sun. So the star is not special. The planet orbit is special. And we believe the planet is not special either. The planet is, in a sense, very similar to what we know about our own giant planets, Jupiter and Saturn, made of gases, mostly hydrogen and helium, fairly large, cloudy, semi-liquid object which doesn't have a solid surface like the Earth or Venus or Mars does. But this is what we call a hot Jupiter. And the big question here, again going back to the outline of my talk, is how do planets actually form and survive? Do we have to rethink our understanding of planet formation? And the answer is yes. In the last 10 years, there has been a lot of rethinking, revisions, and work, and there is still a lot more work to be done on understanding planet formation in a way in which we really didn't understand before. It is difficult to actually do that. It involves more than one discipline. It's not just within astronomy that this will be resolved, most likely. It requires a lot of calculations, like the one Mike showed you for stellar encounters, which have still to be made. You would ask, well, do we have any idea how a hot Jupiter could be produced? And yes, there are some ideas now that we know they exist. People have quickly been able to come up with ideas. And one of the ideas that is most worked on and believed to be the explanation for these unusual orbits that we discovered so far has to do with the formation of planets in a disk. As Mike already described this for you, after the formation of a star, the young star is still surrounded by a few percent of the material left over from its formation, which is in a disk rotating, flattened disk rotating around its star. Planets form in that disk, and some of them grow to become very big, certainly almost as big as Jupiter or Saturn. A computer simulation of a disk which is seen face on from above, so to say, is what you see here. The star is in the center of that disk, and then you see the planet below the star as a small white dot, which has eaten away a certain amount of material from that disk already. That's the material from which the planet has been accumulated. But what is also important to notice in this view graph, these spiral density waves that you see both in the inside and the outside of the disk, which are gravitationally excited by the orbiting planet. Now, there is hence an interaction between the planet and the remaining material in this disk. And in the past 10 years, it has been shown that this kind of interaction can lead a planet like Jupiter here to actually slowly move inwards, that is, lose some of its momentum and slowly spiral in towards the star. So in a sense, there is a possible way in which you can create orbits, although big planets have to be formed far away from the star, but they could eventually end up parked very close to the star. So that's one possible explanation, and very likely explanation for those unusual orbits that we now know exist out there. Now, of course, you have to realize that this amazing diversity that we see there is also biased, as we would say. It's determined by the tools by which we discover and study those planets. And on one hand, we have very new environments to study, which we never knew existed before. There are no such planets in our solar system, and there are no such objects that we knew or could study before. Jupiter's so close to their stars. So you have very interesting new physical environments to understand and model and study. And you can do that by doing spectroscopy, by studying their mean densities and atmospheres, and work with many colleagues in other departments, which is one of the beauty of this research that we do nowadays. But you have to understand that these unusual planets that we discovered for the past 10 years are also reflecting the methods by which we discover these planets. And what I mean by this is that these methods have actually allowed us to discover, at least in the beginning, planets which are very close to their stars, simply because it's easier to discover such planets. And in order to, for you to get an idea of what this means, I have to describe for you two of the methods which have been successful in discovering planets in the last 10 years. The method that has been most successful, and in fact began this new field and revolution in planet discovery, is called the Doppler shift method, or the stellar wobble method. And it is simply a way of being able to detect an unseen planet. And you have to know that up to now, most planets around nearby stars are virtually unseen. Even the largest telescopes are not yet capable to actually see a planet right next to a star by virtue of the very bright star, which does not allow you to pick out the very faint light from the planet. If the star was not there, planets are not that faint. Our telescopes could detect them and study them. But the star being so close to the faint planet doesn't allow us yet to do that. And there are some very clever techniques which are now developed to circumvent this. But it will take probably a couple of more years until this really starts working. So in the meantime, what was done 10 years ago and what has been successful so far is actually doing it in a completely different way. You're not trying to see the planet, the unseen planet. You're trying to see the effect this planet has on its parent star. And the effect the planet would have on its parent star is purely a gravitational pull, going back to Newton's law. That is, there is a slight pull that the planet would exert on the star, and if you could observe the star, which you could with your big telescope, you would detect this slight pull back and forth in the Doppler shift of the spectrum that you can observe of that star. In other words, you can see that dance, that wobble, which is the telltale sign that there is an orbiting planet around it. And this is the technique which proved successful. But you can immediately see that if you have to wait for 12 years for Jupiter to go around the sun, it will be a very difficult project to do. So obviously you will pick out the hot Jupiters first. That is Jupiters which are much closer to the star. In fact, you gain 2 times there. First of all, you don't have to wait for 12 years or after retirement to actually be sure that this is a planet. But more importantly, if you're closer to the star and you have the same mass ratio between star and planet, you actually have more of an effect on the star. Makes sense. You're closer to the star, so the planet exerts a stronger pull, and hence the dance, that the wobble, is more easily detectable. So it is not at all surprising that the first planets out there that we've been able to detect and discover and study are hot Jupiters. But the sheer number of those already discovered tells you that there are quite a few of them. So it is not simply because our methods have given us somehow a planetary universe out there. We know that there are quite a few of them already, sheerly by the numbers that we have detected. There is another method which will also detect mostly hot Jupiters, and that has become successful more recently, and that's a method which uses eclipses, or more particularly transits. That is, this is the phenomenon or the event when a planet passes in front of its parent star. And transits are events which are known to humanity for quite a long time, way before we could detect a planet around a nearby star. We could observe transits in our own solar system. And this is Venus passing in front of our own sun. And as observed in this case from the Netherlands, but it was also observable partially from here, from Boston. That doesn't happen very often. Mercury is the other planet that we can observe in transit. And what is really happening here is that we see the projected dark disk of the planet across the bright surface of the star. Now imagine that you could observe that around a different star. And that will happen sometimes. There are many stars out there. There are many planets. And some of them will be just aligned. So this will happen for us as observers here in the solar system. Well, if this was to happen, then you're not going to see the picture of a planet passing in front of the star. The star is a point of light. Instead, you're going to see the star dimming just slightly. The brightness of the star will dim just slightly. In fact, it turns out that this slightly is not that slight. It's modern technology allows you to detect this kind of dimming or dropping brightness. And in fact, you can already calculate in your head, if you like to do this kind of calculations, by how much the brightness is going to actually dim. It will be the ratio of the two areas, the dark area and the bright area. The dark area takes out a certain amount of that bright area. Again, all you see is a point of light. You see many points of light. You see the stars over many, many nights. You keep observing them with your telescope. And then some of those stars will show dimmings, periodic dimmings. Every once in a while, the star will blink for a few hours, and then again, and then again. And that's the first indication that maybe there is a planet which is passing in front of it. Of course, that turns out is not enough to be sure that it is a planet. And so you have to do something more. You have to go back to the stellar wobble method and just confirm that this is the case. And here, I want to show you some data as it really comes out from our research so that you get a feel for it. Here is an example of the light dimming that I was just showing you in the animation which you saw before for a particular star. Again, not a very romantic name for it, but that's a star which shows very periodic dimmings like this by about 1.5%. You see this is percentage here, so 1.5%, which tells you immediately that if the star is a solar-type star, which we know it is, then the object which is obscuring it, transiting in front of it, is about 1/10 of its radius, which is exactly what Jupiter is. So we have an object the size of Jupiter passing in front of a star like the sun. And lo and behold, when you go and use the Doppler shift or the stellar wobble method, which is what you see on the top graph here in radial velocity, the Doppler shift, back and forth in orbital phase, it does exactly what you expect. At the right phase, the star is moving back and forth by just slightly, a small amount, which would be due to a planet which has the mass of Jupiter, and we know it also has the size of Jupiter from the dimming. And this now tells you that this is a planet orbiting a solar-type star. Not only that, you now know both the mass and the radius of the planet. So you know the mean density. And the mean density of this one is similar to that of Jupiter. In fact, it's a little bit less than that of Jupiter, but very similar. Except this is also hot Jupiter. It's very close to its star. So why is this new technique so exciting? Well, the reason it's exciting because you can continue exploring that planet. And this has been done for a transiting planet, which I showed you the orbit for that one. And that was the first, which was accomplished with the Hubble Space Telescope. During the short time of 3 hours, while the planet is in front of its star, you could observe with the Hubble Space Telescope its spectrum, the spectrum of the star, and the light passing through the atmosphere of that planet. And what was found is that sodium absorption was stronger, and as expected from the theorists, that indicated that for the first time we have detected the air, so to say, the atmosphere of a planet around another star. This same transiting planet was then observed again, but with a new telescope, like the Hubble Space Telescope, but looking in the infrared, in the thermal radiation part of the spectrum, where you detect virtually heat. And this time, the observation was done when the planet was behind the star. So what you saw there is a dimming, but this time the dimming is not due to the planet in front of the star, but it's actually the planet disappearing behind the star. Because it is a hot Jupiter, it is really hot, and in the infrared you can actually see, it's like those military goggles that you see at night. And it's a very slight dimming, but the telescope, similar to the Hubble Space Telescope, it's called the Spitzer Space Telescope, which is the infrared one, was able to detect that for two actually transiting planets. And that detection was actually accomplished earlier this year, which is to show you the strength of this new technique of discovering transiting planets. But really why I wanted to tell you about the transiting method so much is because it allows us to make a next step. And the next step is really exciting. The transiting method, this dimming method, is technologically the only one today that can actually bring us to the ultimate goal, to detect planets around solar-type stars, which are as small as the Earth. The Doppler shift technique by itself cannot allow you to do that. The Earth is too small compared to the Sun and does not really pull enough gravitationally on the Sun so that we can detect that wobble. However, if the Earth was passing in front of a solar-type star, technically we would be able to do that, to detect that today with such telescopes. And the transiting method would allow us to accomplish this. And you may ask, well, why is this such a goal for us to find planets like the Earth around other stars? And this brings us to the bigger question, the question of what is really the pathway from stars to life, understanding the origins of life in the universe. And astrophysics is really providing those initial conditions, the stage to that. And we believe now we have come to the point where technically we are ready to do that big step, to show you evidence to find evidence and discover planets like the Earth around other stars, and hence be able to go the next step and study them and to see what do they look like, what is on their surfaces, what is in their atmospheres. And that question is bringing us to trying to understand the connection between planets and life. Planets are unusual objects in the universe, which are stable over long periods of time and have moderate temperatures in which complex molecules can exist and can actually try out different complex reactions before they are destroyed, which would happen in outer space due to radiation and other violent events. So there is this coevolution of a planet and life that we have seen here on planet Earth. A very strong coevolution. Planet Earth started as an astronomical object, and today its surface is completely transformed geologically by the existence of life. And the next big question when we talk about the coevolution of planets and life and the Earth is, what about Mars? And Mars, fortunately, is now a place we can visit and study this kind of questions. In fact, this is, as you know, right now accomplished by the studies of the rovers, Spirit and Opportunity on Mars. For the first time, we've been able to, in fact, do geology on another planet in the same level of detail in which you could accomplish on some outcrops here on the Earth. And that's these layers that you see here show you those different distinct sedimentary layers. Some of those layers are due to precipitable water sedimentation. So they occurred in water environments. And by the way, these are the samples which the rover took as it was descending down the face of this crater. So these are the tracks of the rover, and you see the samples that it took along the way in order to study them. So you see distinctly those layers. A very exciting time for the study of the possibility and habitability of other planets, in particular Mars, to life and biological activity. Again, many very rich, for geologists, layers of sedimentation here. So basically, we want to be able to make that step, but in the solar system, that's about it. You have Mars, then you have Venus, and we know Venus' surface is inhospitable, and then Mercury and everything else is more like the moon, where we've been already. So Mars is our best bet here in the solar system, but then in order to understand the big picture of what is possible or not possible in the universe as a whole in terms of origins of life, we have to go and study other planets like the Earth around other stars. We'll be able to see different environments, number one. Number two, we will be able to see similar planets to Earth at different ages. Planets like the Earth, but early on in the evolution of the Earth, and planets like the Earth, but much later in the evolution of the Earth. We'll be able to follow that whole sequence of young planets in which life may be just beginning, and very old planets where something must have happened. Either life took over the planet like just planet Earth, or we don't know what future of life could be on a planet which evolves like this. So basically, one thing which I want you to get away from my talk is to understand that from the perspective of an astronomer, planets are indeed special places in the universe, very unusual special places. And what we call biological activity and the transition from chemistry to biology seems to be most likely possible only on objects like planets. And the other thing which I want you to take away from this talk is that we are very, very close to that exciting moment, I think, in the next few years, to be able to study planets like the Earth around other stars. Not just discover them, but study them. And this whole research is going to tell us a lot about the future of our solar system and generally understand how planets form and survive around other stars. So I would have told you now that we have to go to space and find those planets by using the transit method, and that will take a few years, probably about 5 to 6 years from now, to be able to detect such planets. And the plans are actually underway to accomplish just that. But in the meantime, technology has been improving so well that things are happening even as we are preparing for those space missions. Just 3 months ago, the group out in the West Coast, in Berkeley and Santa Cruz, managed to detect the first planet which we now could call an Earth-like terrestrial planet with the Doppler shift technique. And what went there for them was that this was a planetary system which they had observed for many years now, almost 10 years now, and the star is very small. So the Doppler shift technique gave them an opportunity to see the stellar wobble due to this very small planet. It also has a funny name, GJ876. It's a number, but it's a very exciting discovery because it shows you that the moment of time when we'll discover an Earth-like planet is coming closer. Of course, this is an animation just to give you an impression of what is happening. This is a star, GJ876, which already has had 2 planets known around it. And notice that the star is somewhat dim, reddish, and small. This is, in fact, what we call an M dwarf. The star is about 3 to 4 times smaller than our own sun. It's a little star in our neighborhood here, which has 3 planets. The 2 other planets were discovered several years ago, and they have periods of 30 and 60 days. So they're like hot Jupiters. They have the masses of Jupiter and Saturn, and they are in orbits which are fairly close to this small star. But the new planet, which was discovered this summer, has only the mass of about 8 Earth masses. There are no such planets known in our solar system. There are the Earth terrestrial planets, which is the Earth, Venus, with 1 Earth mass. And then you jump all the way to Uranus and Neptune, which have 14, 15 Earth masses of material. So something in between does not exist in our solar system. So in a sense, this is the first. We now, for the first time, have a planet of a type which we've never seen before or imagined before. Of course, this is an artist's conception. We don't have a picture of it. But it is very exciting that we are coming close to that moment when we can detect such planets. And, you know, the whole point here is that the observers do their work and they manage to detect and find these planets. In the meantime, theorists, of course, have theories about them and tell you what the observers should be doing right or wrong. So we don't have an image of this planet, but we have models for it. We call them now super Earths because they're so much bigger than the Earth in terms of mass. 5, 6, 8, 10 times bigger than the Earth. But they're still very similar to the Earth. So what we believe is that these planets have a very similar structure to that of the Earth. See, this is density here in kilograms per cubic meter, just to keep with the European origins of the right lecture series here. And the radius is in kilometers. So there is the Earth, which at the surface is a little bit more than 6,000 kilometers in radius. That's the center of the Earth, where the density is high. And there are several transitions, the core, the mantle, and there is the surface of the Earth. So then if you take larger Earth-like models, which interestingly nobody had bothered to calculate before because there are no such planets in the solar system, so why do you need to? There is an 8, the blue line here is an 8 Earth mass model, which is about 2 times, but not exactly 2 times larger in size. But very similar structure. Look at the structure in the upper crust, and then there is a very large mantle, and then there is a larger core, but still a core here. The interesting thing about this planet is that it will have a crust with continental crust, but much more tectonic activity, which somewhat makes sense. There will be continental motions will be faster, a lot of earthquakes and volcanoes probably. The interesting thing of the core, which you can't see on this graph, is that it's going to be mostly solid. So the magnetic field of this planet is not going to be as strong as that of the Earth, most likely, which has implications for even for life. So we're having a lot of fun with these new planets. And I'm sure there will be a lot more new things to study very soon about this. But as I said, just to conclude, we have plans now, much bigger plans, to go out and really study planets like the Earth, not 8 times super Earths, but real Earth-like Earth twins. And that mission is called Kepler. It's a NASA mission. It's being built right now. It's a space telescope, which is basically a very large digital camera, which is going to use the transit method, observe many stars, 5 years, without any interruption, and look for all the stars which blink. And those that blink regularly will follow up from the ground. And we hope, and this camera should be able to actually see planets which are as small as the Earth, even smaller. And our goal will be happy if we detect a few of them, but there should be at least a dozen really Earth-like Earth twins in our sample. And that will happen very soon. And then, once we know where they are and what they're like and how many of them are there, hopefully there will be many, at least a dozen in our sample, then come the plans which are further in the future to actually go and study them. And all this has to be done from space. The atmosphere is too much of a blurring medium to do such very precise and difficult studies from the ground. So NASA has, again, plans to accomplish this once we come for this. These plans are still under development. This is one of the previous ideas of how this terrestrial planet finder, or more likely study, a terrestrial planet surveyor will look like. It may not look like this. The plans, the design is still underway. So basically, and I hope I convinced you, we're at the beginning of a journey, a big journey to discover places like home around other stars in the universe at large. And the exciting thing about it, it really, in reality, it only started 10 years ago, and it's moving so fast today that we all can be witnesses to it. And there is nothing more exciting than that. And I'll end here giving a clue to a hook to the next week's talks, which will talk about the possibility for life and its origin. Thank you.
Okay, so before we go to the panel, Mike will make one more 3 or 4 minutes add-on to what Dimitar has just noted and show, I gather, another simulation. Is that right? We'll go to you.
Yes,
And
and
we'll
I
need,
probably have to pop the computer open.
Yeah, I'm going to close this carefully.
All right.
And take that down. You can put yours up.
Okay.
Is it working? All right.
Very good. The one word we don't want to hear here is whoops.
See if that works. Good.
All right. So now coming back to the salacious part of the talk. What we do, Eric, do you have the pointer?
It's rubber button right up there.
Great, thanks. What we do is we take a special computer board that is what we call a teraflop telescope. It's a computer board that can calculate only one thing. It can calculate GMM over r squared, that is the force of gravity between two particles, but it can do it 1,000 times faster than any Pentium or pretty much any computer around. And if you do 10 to the 18 or 10 to the 19 floating point operations, what you can do is you can take up to 200,000 stars and you can follow them realistically for 10 billion years and watch the influence, the gravitational influence of every star on every other single star that's there, and follow the evolution through stellar evolution simulations of every star at the same time. And that takes up to a year to do for a single star cluster. When we do that, we create the closest approximation, I would say, to reality in astrophysics, stellar astrophysics certainly, that exists today. This is what astronomers call a CMD, a color magnitude diagram, and it's a measure of the brightness or the luminosity versus the temperature. This here is an 67, an observed color magnitude diagram of M67, and this is the simulated color magnitude diagram of M67. Every dot is a star 4 billion years after the cluster formed, and the details aren't important, but the important thing to note is that this track of stars is reproduced with incredible fidelity, and even the collided stars, these teenagers in the old folks' home, are reproduced with astonishing fidelity inside the cores of stars. What we do find along the way, and this really is an accident, this is something we had not expected when we were doing the simulation, is the phenomenon that we now refer to as stellar promiscuity. By stellar promiscuity, well, it's actually easier for me just to tell you what happens than to go into the salacious details, and that is the following. We start at 0 megayears with a 6.9 solar mass star and a 3.1 solar mass star. Days, these stars are separated by a tremendous distance in a slightly eccentric orbit. Now, why these numbers? Because we take 100,000 stars or even 200,000 stars in some of our simulations, and we take all possible, or most possible, separations, mass ratios, eccentricities, stick all of these stars into a star cluster, and let the computer go. So we're not trying to simulate any given star cluster star by star, but statistically we want to see what's going to happen in the large. Well, after 60 million years, the eccentricity has gotten away. That is, the stars have managed to circularize their orbit, and mass gets transferred from the high mass star to the low mass star, and some mass is lost, and you end up with a 1.3 solar mass white dwarf, that's the dying or dead star, and a 3.1 solar mass original star. You get another episode of mass transfer after 430 million years, and the final state of this star, which now has not a 9,500 but a 9,100 day period, is a 1.3 solar mass white dwarf and a 0.8 solar mass white dwarf. And these stars will actually merge. They will come together because they're going to lose gravitational radiation. But it's only of academic interest because it'll take longer than 10 billion years, not 10 to the 10 gigayear, 10 gigayears, 10 billion years to merge together. So in essence, nothing happens. That's the end of the line for this pair of stars, if it were just an ordinary isolated pair of stars, but it's not. 200 million years later, another star comes along, a 2 solar mass star comes along and runs into this star pair and forms a ménage à trois. That's unstable in human terms. It's also very unstable in stellar terms. And the same sort of thing that happens in human terms also happens in stellar terms. You get lots of dancing around the issues, the occasional lie and close encounter, and finally the ejection of one of the three, because a ménage à trois is ultimately unstable. And the ejection in this case turns out to be the lightest star, the 0.8 solar mass star. So now you're left with a 2 solar mass star and a 1.3 solar mass star in an even more extended orbit. But it gets perturbed again by another stellar encounter. And this star turns into a white dwarf, and the two stars merge, and they exceed a magic mass in astrophysics called the Chandrasekhar mass. These two stars actually implode because they become too massive, and they form a supernova. This is a dynamically driven supernova. It's a new kind of supernova, and we are finding more and more and more of these in our simulations. In fact, we are sticking our necks on the astrophysical chopping block and predicting that a significant fraction, and maybe even a majority of all supernovae, type 1a supernovae, are made in these kinds of encounters. That is, in promiscuous encounters between stars. Now, how promiscuous can stars be? Well, just as promiscuous as people. We start with 20,000 stars in a cluster. We have 500 cases of what we also call stellar infidelity. And 15% of the stars are involved in promiscuity. Here, when we up the density, it becomes 50 or 60%, perhaps equal to what goes on, at least that's what Kinsey tells us, and other researchers in the American public. Now, some stars swap partners only once, but others twice, 3 times, 4 times, and there was one crazy star that changed partners 22 times. A merry life. Let me talk just a little bit about planets in star clusters to follow on to what Dimitar said. Certainly, the most accepted theory of how hot Jupiters migrate is via these interactions with the disk. That really seems to be an elegant way of making the stars, planets migrate. But of course, there is the nasty and ugly question, why didn't Jupiter migrate? Why don't all planets migrate? How did we end up with a solar system that looks like we do? So partly motivated by that, and partly because we have the hardware to do this, we have added 100 planetary systems. Well, simplified planetary systems. You know, just like a chicken is spherically symmetric, we've taken solar systems that are the Earth, Jupiter, and Saturn only because that's all we can manage. The computational problems are so fierce. And we've put them into these star clusters. So while we're evolving our star clusters, we're also evolving planetary systems to see what happens. And here's a quick peek. This hasn't been published yet, so please put your digital cameras away. Saturn is always in blue or aqua. Jupiter is always in green. And the Earth is always in red. And what I've plotted out here is the eccentricity versus time and the semi-major axis, the distance from the host star versus time. And wildly different, this is simulation 1, simulation 2, simulation 3, or rather solar system 1, 2, 3. And it just depends on who comes close. That is, if you're a solar system and another star comes close to you in a star cluster, and these things do happen, you get gravitational perturbations. You change the orbits. And sometimes you make the massive planets wander inwards. Sometimes you make them wander outwards. So here, for example, is a case where Saturn becomes wildly eccentric, nearly 1, goes up and down, and its semi-major axis. Saturn started here. It goes 2.5 times as far away. Then it comes closer than it was, up, down, up, down. It can approach the star, recede from the star, and so on. Here's a case where Jupiter actually lived less than 1 million years. Jupiter got a kick and was thrown right out of the system. Not what you might expect. Here, on the other hand, is a case where the Earth and Saturn were ejected very quickly, and Jupiter went oscillating wildly back and forth. But in this case, its eccentricity oscillated, but Jupiter started out at 5 Earth distances and dropped down to 1 Earth distance. In fact, it got so close to the Earth that it ejected the Earth, and we ended up with a hot Jupiter. Finally, here's a case where the Earth itself oscillates wildly in eccentricity. So the point here is that there is at least one other way, and probably multiple other ways, of making these hot Jupiters. If you're born in a star cluster, as the Sun almost certainly was, planets can be rattled around, and perhaps the miracle is that the solar system is so organized, so stable, so beautiful, so symmetric, and that we're actually here. Okay. So I think we're going to do the...
We're going to pause for a minute. We'll bring up the lights. We'll let you get up out of your seat for a 7th inning stretch, but don't leave, and then we'll form the panel. We'll be back in 1 minute. Thank you, Michael.
Okay.
In my head, repeatedly, as both speakers trotted out their materials, although I don't think either one of them mentioned dark matter. And the reason I mentioned dark matter is that in grad school, one of the guys I studied with, Ed Purcell down at Harvard, was always of the opinion that, the dark matter problem can be solved by interstellar basketballs. He said you'd need a lot of interstellar basketballs, but he noted repeatedly, as I do in my class now, and people find it fascinating, that we have instruments in our arsenal of astronomical devices that can detect things as small as atoms, spectroscopically, and as big as stars, generally, if they're big enough to be radiating. But objects that are in between, like dwarf stars, about which you talked about quite a bit tonight, right, and extrasolar planets, about which you're making your money on now. Those are objects at intermediate in size and scale between atoms and full-fledged sun-like stars. So is it not inconceivable that Ed Purcell was not being as facetious as he might have thought he was, in that maybe there are a heck of a lot of red dwarfs? You look in the globular clusters. We used to think before we looked at the edge of the globulars with Hubble that maybe there would be an astronomical number of red dwarfs. And you're finding increasing numbers, I'm convinced now, at the rate at which you're finding extrasolar planets, that there are a lot of them out there. But is it not inconceivable that we could begin to make a dent or even come considerably close to solving, because we will have to solve eventually the dark matter problem,
right,
by merging both of these new kinds of objects that you're talking about in the larger inventory, dwarf stars, extrasolar planets. What do you think?
No. Nice try.
Because they're very early?
That's one problem.
You know,
the dark matter isn't made of you and me. It isn't made of protons, neutrons, and electrons. It's definitely made of something else. Maybe not all of it. Right. Maybe 5 or 10 or maybe 20% is made of baryons, made of stuff like you and me. And that would still be a heck of a lot of stuff, maybe more than the visible stars that we see around, almost certainly more than the planets. But there's several different lines of observation really would strongly suggest that it can't be baryonic. So that's number one. Number two, I think that there are enough surveys, at least for white dwarf stars and red dwarf stars, certainly in the neighborhood of the sun. And people I work with are doing that. Other folks are doing excellent surveys that have pretty much ruled out either white dwarfs or red dwarfs as very significant contributors to this invisible stuff. So, nice try, but no cigar.
What do you think? Do you agree with him?
I agree totally with him.
Oh,
I would say also that our own solar system, as a planetary system, has actually played a little role to tell us that whatever dark matter is, it doesn't clump very much, and it's not very, there isn't very much of it in our own galaxy, at least where the sun is. Because if dark matter, which still has a gravitational pull, was pervasive, and there were clumps of it passing through the galaxy, then a lot of the very fine-tuned orbits of small bodies in the solar system, especially further out, beyond the orbit of Neptune, would be disturbed in a way in which we don't see them disturbed, just like passing stars. And we know that passing stars In a similar way, we can say there isn't that much dark matter, which has been in our vicinity, at least for the last 4 billion years. So it's still a mystery to be resolved in some other way, but it's not runaway planets.
Not likely to be in the stellar basketballs.
No.
You mentioned Pluto.
Yes.
One other lick before I open it up. I'm arguing currently with my publisher now, a textbook publisher, because I want to, in the next edition of my book, declare that there are only 8 planets in the solar system.
Great.
And I hope my publisher is watching on the internet, because we've got to support it here.
Absolutely.
I mean, a couple of years ago, there was an object comparable to Pluto's size and twice as far away. Now, this past summer, we've got an object that's roughly twice the size of Pluto and twice as far away.
Right.
If Pluto's a planet, those other 2 objects are planets, and many more that will be found are planets.
It's worth remembering that in the early 1800s, if you look at the textbooks, the astronomy textbooks in the early 1800s, the solar system grew from 7 to 8 to 9 to 10 to 20 to 30 to 50 planets because the asteroids were being discovered. We don't call those planets today. They're a different class of objects. Similarly, Pluto is the first discovered, and now not even the biggest, of a different class of objects, the Kuiper belt objects, the icy objects on the outer part of the solar system.
But how can we declare Pluto is not a planet without reducing all the 3rd graders across the country to tears? Pluto is the favorite planet.
You probably can't. Life isn't fair. Pluto is not a planet.
I'm with you.
You eventually learn.
Pluto?
I agree with what Mike said. But I don't want to make all the 3rd graders cry. So.
He's kinder than I am, nicer guy than I
Doesn't
am.
want the hate mail that Neil gets.
That's right.
Okay, we should begin to, because time is fleeting, begin to open this up a little bit to questioners. Laura, you have someone right there, I think. Yep. Mike?
Which says that man is a nuisance in space. In other words, when it comes to space exploration, so much of the resources have to be expended in getting man up there comfortably to, say, to Mars and bringing him back. Whereas if you were to take those kinds of funds and put them into sophisticated robots, you would accomplish more. On the other hand, the other school of thought says that there are certain things that only man can accomplish on site, which robots can't. They don't have to be remotely controlled, etc. And they also point another problem that the general public is more interested in funding astronauts than they are robots. Do you
As
have
the
comments
congressman
on
says,
this?
no bucks for no bucks for Rogers. You need humans in space. What do you think? Robots or humans? Do we get more bang for the buck from robots?
You probably get more scientific bang for the buck from robots. I lived and worked and breathed the Hubble Space Telescope for 17 years. I worked at the Space Telescope Institute. That is perhaps NASA's finest mission where astronauts did participate. Of course, there was the Salvation mission. Hubble was almost, I won't say dead on arrival, but had severe spherical symmetry when it was launched. And a tremendously talented team of astronauts saved it, and in many ways saved NASA's scientific reputation in 1993, and have performed refurbishment missions that have made it ever more powerful. That having been said, there are now robots that can be built and in fact should be built to service valuable missions like the Hubble telescope, like the Next Generation Space Telescope, and so on. So if it's just science, on a purely science basis, I think that you probably can usually do better with astronauts. That having been said, the presence of humans in space has provoked us, forced us, pushed us to build very sophisticated instrumentation, some of which has flowed back to benefit us here on Earth and other aspects of pure science. And very realistically, politically speaking, people do want to see other people go to the moon and especially go to Mars. So I don't think that we're going to have a space agency or a serious space program without people in space.
It looked to me like none of the machines that you were talking about would require human space.
That's true, but I would disagree about certain missions like geology on Mars. If there is no conceivable way in which we can accomplish as much as a couple of astronauts with knowledge of geology could accomplish just in one single visit to Mars. These beautiful pictures and the samples that our 2 robots are still taking on Mars today are an enormous step forward, but nowhere near what could be accomplished by a simple visit there and just using the old-fashioned hammer of the geologist. It's a human being can accomplish so much more on Mars.
That was the NASA police hovering over you. Zach, you have a question or somewhere? I can't quite see. Maybe there's someone way down here in the front. A couple of gentlemen down here. There you go.
Is there a continuum in your understanding of the formation of stars and the formation of planets? I'm thinking that most stars are double stars. Is the distance between star formation so different than the distance between star and planet formation that you think about them separately, or do they merge in your understanding?
Stars are born with an enormous range of separations. In particular, there are stars that are born Siamese, that is actually physically touching each other. And then there are, and that means the centers of the stars are perhaps 1 million miles apart, because the diameter of a star is typically 1 million miles. And then there are stars that are up to 10 million times further apart than that. That's about the range we see in our galaxy. You can't get double stars much further apart than that, because then the tidal forces of the galaxy tear the two stars apart. So that's the separation range. There cannot be planets in certain orbits around very close double stars, because the planets don't know who they belong to. They get tugged both ways. It's not like two parents. It's perhaps like two warring parents. But if the two stars are far enough apart, then there's no problem having planets around each. And Dimitar knows better than me, but I believe there are now at least one, maybe more, examples of planets, exoplanets, that have been detected in the environs of binary stars.
Yes, indeed, there are several such planets in binary systems. And there is a continuum to their formation, as you asked in your question, except there are certain configurations or orbits which obviously would be very unstable and would not support planetary orbits. It will take a while for us to be sure that this doesn't happen. People don't look for planets where they wouldn't expect them to be, and hence we have very few cases in which we can tell you, we know this binary system of stars has no planets around it. But certainly there is a continuum with particular orbits which are excluded by the dynamics.
Is there enough stuff in your Jupiter-like planets to turn them into stars?
No.
Be brief. There's another gentleman right in front of you here. Where's the mic? Back? There we go. Yep. Laura, where are you? Okay. Do you have somebody?
With 100-plus observations of extrasolar planets, what is now the estimate of the fraction of stars in the galaxy that have planets, and can anything reasonable be said about the fraction that have hospitable planets?
Very good question. We don't know the answer yet, but we have much better guesses. Yeah, it seems. All right. We do have much better guesses today than we had 10 years ago. First of all, when you say planets, remember that we haven't reached the ability to discover planets like the Earth, or especially smaller things like Mercury yet. So we know very little about that fraction yet. And I would call habitable planets planets which resemble terrestrial planets in some form or another, or at least moons which circle bigger planets which are like that. When it comes to Jupiter and Saturn-like planets, the fraction is at least a few percent and probably larger. And that we don't know yet fully, partly because it's been only 10 years. But if you want to detect the existence of planets like Saturn, you need a lot more.
They're de-wiring you. I thought Colin last week was bad. Are you done with that? All right, I haven't either. He's holding on.
If the number is truly just 3%, that's all it is. If it's only 3%, and there's 100 billion stars in the galaxy,
Centauri, call it.
That means that if it's only 3% of 100 billion stars, that's still 3 billion planets wandering around in the Milky Way galaxy. A lot of planets. There must be many more.
Great. Laura has a question right behind you.
How does metal content of a star influence planet formation?
Good.
Another very good question. It does. As you understand, a lot of what a planet is heavy elements. Even planets like Jupiter and Saturn have a lot of heavy elements in them, at least 10 times more than what its parent star, the Sun, is made of. And that means that more metals, more planets are likely to form. Also, there is an expectation that it's easier to agglomerate the material in that disk from which planets form if there are more dust particles, small particles, which are mostly made of metals, silicates, things like that. So that's a good question, and it seems that the evidence goes in that direction.
The observations go that way too. That is, the more metal-rich a star is, the more likely it is to have planets.
I would like to ask about the comment that the stars are the ones that are like nuclear reactors. My understanding is that all of the heat that we're getting from this Earth is because of nuclear reaction going on in the center of the Earth. And so, unless I've got it wrong, we're sitting on top of a huge nuclear power plant. Is that wrong?
That's wrong.
Well, there's...
And so what's the difference between
You're
the Earth?
partially right.
Radioactive decay.
Radioactive decay is a major source of heat on the Earth and all the terrestrial planets, but it is not the main source of heat. Certainly not today.
What is?
It's still the cooling of the Earth from the initial formation 4.5 billion years ago.
It is interesting, though, in your definition of a star, there was a self-gravitating body which has its own internal energy source. One could say, nonetheless, is not the Earth, a self-gravitating body that does have its own internal radioactive energy source. That's a fair statement.
But isn't it true that the first reasonably accurate estimation of the age of the Earth came about because of analysis of the heat from the center of the Earth by Rutherford?
Kelvin.
Yes, Kelvin made an estimate which was Ward Kelvin.
Kelvin was wrong.
And that was the wrong estimate at the time.
Very wrong.
Again, the reason the Earth is as warm in the center and in the surface today is because the Earth is a very bad conductor of heat. So it is capable to retain the heat in the core for a very long time.
Two brown dwarfs collide. Do they form a star?
Excellent question. If you take two brown dwarfs and crash them together, which can happen in the core of a globular cluster, if the sum of the masses, the retained mass, is in excess of 7.5% the mass of the sun, the answer is yes. You will take two objects that were a star and turn them into a star.
Up here in the back in the bleachers.
Hi, yeah. My question is a little bit different, but you mentioned earlier how like the basis of life as we know it, or there's a possibility of life in some other possible, I guess, maybe basis or something. It seems like the nature of carbon as the element we know it is the only feasible like core element that could biologically form the structures that could bring about life. And you hear in sci-fi movies like silicon could be the next thing, and it seems just ludicrous. And I was wondering if you knew any modern theories that could even propose something along those lines of life in a different basis.
That's a good question to which, unfortunately, I can't give you an answer. But what you say is thoughts about the matter which have been around, and people have thought about this for quite a few years today. Indeed, carbon has a very special atomic chemical structure which allows it to form complex molecules as it does. But we don't know yet what are the different pathways which can lead to complex molecules which are able to perform the functions that we call biology or biological functions. And this is currently a new field with a lot of active research. My expectation and hope is that it will take at least 10 to 20 years to sort this thing out, but there is a lot of interest now in the chemistry and biology community to accomplish this. So just so you know, there is no modern theory which is different from what you already know about the origins of life, but there are a lot of possible opportunities to understand a lot more than we know now.
The question of silicon-based life, other than the one that might be on inside of your machine at home, on germanium-based life, would be a good one to pitch next week to Lynn Rothschild, who is an expert on chemical evolution and the pre-biological steps that have led to life as we know it. And she has thought about, I think, more generalized life that might exist in alien environments.
Let me add one point to that, and that is, rather than look at the molecule which might be the basis of life, let's think for just about a minute about what solvent might be available. You know, we used to think that it was a necessary condition to have sunlight in order to have life. Well, down at the bottom of the Atlantic or Pacific Oceans, you have no sunlight, and you're just teeming with life. So the essential element, at least on Earth for life, or the essential compound is H2O, is water. And water is a wonderful polar molecule. Its charges, the two hydrogens and the oxygen, are separated, and that acts as a kind of wonderful solvent. There are probably only two other common solvents in the universe, just because of nucleosynthesis, the way elements are created in stars, that can exist. And those are methane and ammonia, NH3 and CH4. And it's not an accident. Each one of them has hydrogen, 2 hydrogens, 1 oxygen, 3 hydrogens, 1 nitrogen, and 4 hydrogens, 1 carbon, because carbon, nitrogen, and oxygen are the most abundant elements in the universe by far after hydrogen and helium. So if you take methane or ammonia and put them under very high pressure, they're polar enough that they can be very powerful solvents. And I think we haven't a clue as to what the chemistry or biochemistry of either carbon or silicon or anything else is under these solvents at high pressure and temperature. But those, I think, are interesting avenues to explore.
And I would take the devil's advocate and say maybe the solvents are also a red herring, and we can accomplish those molecular functions on the surfaces of minerals, in cracks of minerals, and things like that. So there's a lot of work to do.
Sagan used to look at the monitor from the Viking spacecraft as it was looking out, and he'd say, "See that rock? How do you know it's not alive?" I mean, it wasn't moving or anything, but it was a good question. Somebody has another good question through here.
Yeah. What I was wondering is, why does the dust around a star form into a disk? And I was also wondering why the axes of stars are so stable.
Good questions. Who wants to handle that?
Okay.
How much time do you have?
Start out with a cloud of gas that's a perfect sphere, or a nearly perfect sphere. The cloud of gas isn't going to remain completely stationary. No matter where you are in the galaxy, there's going to be some torque, some twisting force, a little more pull here than there. So all gas clouds spin just a little bit. As the gas cloud starts to collapse under its own weight, it's easier to collapse in one direction along the spin axis than perpendicular to the spin axis, basically because of centrifugal force. And so there's a preferred direction for collapse. If you're happy collapsing this way, you're going to get flat, but not happy collapsing that way, you're not going to get flat that way. And so you're going to take a sphere and squash it. If you squash a sphere, it turns basically into a bagel if the central stuff gets eaten by the protostar. That's why you end up with a disk. Okay? The second question.
The second question is, why is the axis of spin, or spin axis of a star so stable? That's a good question. In fact, it's not an easy question, but on the surface of it, you can get a simple answer. Well, there is nothing to make it unstable. In other words, the planets are too small, too far away to actually make the axis of the star change its direction. On the other hand, planet axis of spin could be very unstable. Mars is a particular case, which probably over its history in the past few billion years has changed its axis of rotation quite a lot and changed the climate on that planet quite a lot. But stars are very big, and they act the same way as an experiment here with gyroscopes, which you could try out in the museum just across the hall. And you will see how a spinning gyroscope tends to keep its axis directed in the same direction very well.
We're going over here.
In a hot Jupiter star system, would a Jupiter-like planet that's only 4 million miles away be able to retain its hydrogen, or would it be driven off by the heat of the star?
Mm-hmm.
Another good question. And actually, this is a question where there is a debate in. It depends whom you talk to, but there is a slight debate in the scientific community. There is a group which claims that a lot of these hot Jupiters are losing a lot of their mass. Atmosphere is evaporating because of the intense heat, particularly because that heat is accompanied with a lot of X-rays and UV from the star. However, the majority of the calculations which have been done to date tell you that a Jupiter-sized planet at that distance from the star will in fact lose not more than a few percent of its mass, total mass, which is a lot of mass, but not that much. However, if it's a small planet, that could be a lot. That is, if we're talking about a planet which is like Neptune or even smaller, then this in a lifespan of a few billion years could practically evaporate the whole planet. That's true.
If hot Jupiters are formed in other star systems by migration of planets inward, well, why aren't there any hot Jupiters in our solar system?
Well, that's a good question to which I don't know the answer. I have a hunch, and my hunch is that in our solar system, Jupiter managed to form fairly early on, far away, not that close to the sun.
But a good deal farther than where it is.
Yeah, it could have formed just 2 or 3 times farther away than the Earth, as we would say, 2 or 3 astronomical units. And then, I believe, this interaction with the disk would have made it migrate inwards much more so than we have any evidence. The evidence for Jupiter actually moving with respect to its current orbit since formation is none. There is very little evidence that there was any such movement or migration. So that's my hunch. Now, I know Mike disagrees with that, and I'm happy to argue with him.
Maybe that's why.
No, I was just going to add to that that I think we can agree that 2 other things must be true. First of all, the sun must have been born to a very impoverished family. And second, it must have left home very early. That is, we think that all stars are born in star clusters, but the cluster in which the sun was born couldn't have been very rich, couldn't have been very dense, because the whole solar system today is so beautifully laid out, still so coplanar, everything moving in the same direction. There couldn't have been any terrible gravitational shocks early on, and the sun couldn't have remained for a very long period of time in its host star cluster because it would have blundered into another star and the outer planets would have been disturbed. So I don't really know the answer either. It may simply be that as Jupiter and Saturn and all the other planets form, the sun left that environment very quickly, left the place where it was born very quickly. Nobody ever had a crack at it. It was never beaten up by some other passing star, and that's helped keep it stable. But there's still a lot of mysteries, a lot of unanswered questions.
We'll take one more question, but time is fleeting. Please.
All right, you just talked about the planets being coplanar and all having the same spin, but as I recall looking at your diagram at the beginning, that was true for everything except Venus. And why is that?
And to some extent Uranus
also. So Earth-like.
Right. Venus doesn't have a moon. That's the enormous difference between Venus and the Earth. We think, of course, that the moon formed by a collision of a Mars-sized object with the Earth very early on, and that's, in all likelihood, what tipped the Earth's axis over 23.5 degrees and gave us our seasons. Venus may have never had that kind of collision. We don't really know what's happened to its angular momentum, but it has a very slow spin, and the angular momentum is so low that whether it's spinning this way or that way, in effect, it's not spinning. Uranus is tipped all the way over 90 degrees, and it, too, has probably had a giant impact in the past. So there has been some cosmic billiards going on in the history of the solar system.
One more question here from this woman, and then we'll wrap it up. Please.
Is there a place in your scheduling of activities that includes Titan, the moon of Saturn that has an atmosphere that we're presently studying?
To visit, you mean, or with a robot?
The one that was.
Is this a question referring to scientific activities or the Right Lecture series?
No, I think she's referring to your...
There are plans for that in terms of proposals by NASA, but nothing has been decided regarding Titan yet, as far as I know. Maybe
Do you mean
Mike
Titan or Triton?
I mean Titan.
Titan of Saturn.
Right.
Titan.
We've just gone there.
The moon of Saturn.
We've just gone there.
Well, it's been done, but I'm wondering if anything has been learned that makes it fit into the program that you've given us.
Mm-hmm.
It will be difficult to say, even based on what we know from the recent visit to Titan, whether that's relevant to the study of that pathway from stars to life. And the reason for that is that answer that we didn't give to the previous question about the possibility of what is the base of life, carbon or silicon-based and so on. In other words, it is not quite clear to us whether it is beneficial in studying this particular question to go and research or do study on Titan as opposed to on Mars. Mars is much closer to what we know about the early Earth, and at least the early Earth we know that this happened. Titan is a very alien place, very interesting, but very alien place, very much more difficult to study. It's so much farther away. And although it's one of the most interesting places to visit in the solar system now, apart from the Earth, of course, I don't think that we know enough about the origins of life today in order to say Titan is a place we need to visit in order to understand that. That's how it is.
All right, we're moving across the arrow of time. We're about to transition into chemistry and biology next week. But before we leave, let's thank our speakers once more again. Michael and Dimitar. Thank you.